Hello everyone, so today we're going to go over section 1.1, geometric sequences. We'll start by looking at these four sequences here by completing the next two terms. So first sequence we have here 1, 4, 7, 10. So it looks like the next two terms will be 13 and 16 respectively. And the idea here is of course that we're adding 3 to each term to find the next one. Likewise, the second sequence we have 8.5 and then 6 and then 3.5 and then 1. So the next term will be negative 1.5. Oops. And then negative 4. You can see here that we are adding negative 2.5 to each term. Next up, the next two are a little bit different. Here we can see 3, 6, 12, and then 24. So the next terms will be 48 and then 96. And we are doubling the value of each term. And finally, the last sequence here, we have 1 and then negative 1/2, positive 1/4, and then negative 1/8. So the next terms will be positive 1 over 16 and then negative 1 over 32. And we're multiplying by negative 1/2 here. So the first two sequences should be more familiar. They are, of course, arithmetic sequences. So there's a common difference between each term. And then the new sequences that we have in the third and fourth example here, those are geometric sequences, where instead of a common difference, we have something called a common ratio. And it's a number that we multiply each term by to get the next one. Okay, so next up is a few definitions. So we can look at, as it says here, a geometric sequence is formed by multiplying each term after the first term by a constant to determine the next one. It is called common ratio, denoted by the letter R. Okay, so here's another example of a geometric sequence. We have, in this case, 2 times 3 is 6, times 3 is 18, times 3 is 54, and so forth. So the first term is 2. Now it says T1 here. Sometimes the first term is denoted A, and then the common ratio is 3. Okay. So the common ratio is it could be any non-zero real number, and it can be found by dividing any term by the preceding term. So if you divide the fifth term by the fourth one, then the result will be the common ratio. Okay. So next up we have, right, so if we have a sequence where it ends in dot dot dot, then it's infinite geometric sequence because it should continue forever. Whereas the second one, after the first four terms, it ends and it will be a finite geometric sequence. And so that's 4 terms. Also known to have a length of 4. Okay, so if we look at geometric sequences, they could be increasing as the numbers, as the terms are getting larger. So in this case, we have 5 times 3 is 15, times 3 is 45, and so forth. So the numbers keep on getting larger, and so it's divergent because it doesn't approach a constant value. Okay. Second one, we have a decreasing geometric sequence. The numbers are getting smaller. They're constantly being halved. So 1/3 multiplied by 1/2 is 1/6. And then multiplied by 1/2 is 1/12. And then multiplied by 1/2 again is 1/24. And since it is a infinite geometric sequence, it's going to keep on, the numbers will keep on getting smaller, and then it will approach a constant value of 0. So it is said to be convergent. So it is possible to have decreasing geometric sequences that are divergent, and it's possible to have increasing geometric sequences that are convergent as well. So just because it's increasing doesn't mean it's divergent, and just because it's decreasing doesn't mean it's convergent. So it's important to note that as well. And finally, we can have geometric sequences that are neither increasing nor decreasing. In this case, the sequence over here, if we multiply the first term by -5, so 1 times -5 gives us -5, and then multiply by -5 again gives us +25. So you can see that the numbers, they have greater values, but then a different sign. So it's neither increasing nor decreasing because it's changing signs, but it is divergent because the values, well, the absolute values are getting larger and it doesn't approach a constant value. However, it is, of course, possible to have a geometric sequences that neither increases nor decreases, but is convergent. And we'll talk about how to determine if a sequence is convergent or divergent in an upcoming example. All right, so again, sometimes the first term is denoted A. And then since every subsequent term of the geometric sequence is the previous one multiplied by the common ratio r, the second term will be equal to term 1 times r. So this will just be AR if we use the alternative notation. Here, this third term is the same as the second term times r. However, we know that the second term is just the first term times r. So this would be term 1 times r, which is term 1 and then r squared, or in some textbooks is also known as a times r squared. And it carries on forward. So the general term of a geometric sequence will be Tn is equal to T1 and then r to the n minus 1 power. Right? Because, for example, in the third term, you only multiply by the common ratio twice. So it's always 1 less. Again, here, I just wanted to say that this could also be denoted as a and then r to the n minus 1. Okay, so let's look at some geometric sequences. This one we have here, 4374 is the first term, and then the next term is -1458, and then 486, and then -162, and so forth. So it says to identify the common ratio r, and the way we can do that is to divide two consecutive terms. So what I mean is the second term is equal to the first term times r. So the second term divided by the first term would just be r by itself. And then, of course, in our case, in our example here, the second term is -1458. And then we divide it by the first term of 4374. And that will give us the r value, which would be, let's see, -1/3. Okay. And then it says to determine the ninth term of the sequence. So the ninth term will be the first term and then r to the 9 minus 1 power, right? We take the first term and then we multiply the common ratio 8 times to get the ninth term. All right, so in this case, the first term is 4374, and then negative 1/3 is the common ratio to the 8th power. You can use a calculator to figure this out, and the result would just be 2/3. Okay. And the last part, it says here to identify the sequence as convergent or divergent. It is convergent. As you can see, the absolute value of the terms are getting smaller. It is approaching 0. And what we're going to be looking at to determine convergent or divergent is the common ratio. So since the absolute value of r is less than 1, so the magnitude of the terms will become smaller and smaller as we go. In other words, a geometric sequence is divergent if the absolute value of the common ratio is greater than 1. Question we might have at this point is, what happens if r is equal to 1? So it is interesting to think about what happens, right? Because if you just multiply it by a common ratio of 1 or negative 1, if you just multiply by 1, then of course each term will be the same number. Then it's just a constant sequence. And then if it's negative 1, then the number just alternates. So let's say the first term is 3. Actually, I should probably write this down. So examples here. If we have a geometric sequence where the first term is, let's say, 3, and then the common ratio is 1, then the sequence would just be 3, and then 3 times 1 is 3 again, and then 3 times 1 is 3 again, and so forth. So it will converge to the value of 3. Now, likewise, well, that's a little bit different, but let's say if the first term is negative 3, I guess, but the common ratio is negative 1, then this happens instead. So we'll have negative 3 as the first term, then positive 3 as the second term, and then negative 3 again, and then positive 3 again. So it doesn't converge to a single value, but it's a predictable sequence, so that's interesting. So a little bonus example here. Okay, moving on. In a finite geometric sequence, the first term is 2 and the fifth term is 512. Okay. it says determine the third term and the sixth term, and then the last term of the sequence is 524,288. All right. How many terms are in sequence? All right. So now the fifth term, t to the fifth power, is equal to t1, the first term, and then r to the 5 minus 1 power. So the fifth term is equal to the first term, and then multiply by the common ratio 4 times. So if the fifth term is 512 and the first term is 2, we can solve for r. Okay, so this will be, let's see, 512 divided by 2, that is 256. And then r to the fourth power. And it looks like we need to take the fourth root of 256. Okay. So notice here, it is possible to have r be 4 or negative 4. Right, so if r were positive 4, then the first 5 terms would have been, just going to list it out this way. Actually, it would have been 2, and then 8, and then 32. Let's grab a calculator to do this. 2 times 4. Right, and then 32. And then 128. And then the fifth term would be 512. So that fits the description. Alternatively, what if we had the r value be negative 4? Well, then it still starts with 2, but then it will be 2 times negative 4, which is negative 8. And then negative 8 times negative 4 again gives us positive 32. And then multiply by negative 4 again gives us negative 128. And then multiply by negative 4 again gives us 512. So both r values will make this finite geometric sequence work. Okay. So your question might be, well, which one do we choose? So hopefully, if it comes to an assignment, we'll try to avoid these ambiguous cases where 2 different r values are possible. It's a little bit odd, but that's okay. Okay, let's continue, because it gets a little bit more interesting if we were to keep going here. So now, in either case, the third term is positive 32. So that's consistent, that's good. But part A also asks for the sixth term here. So let's look at what happens. Okay, so the sixth term will be 2 times 4 to the fifth power, which is, use a calculator for this. Okay, 2048. Now, if r was negative 4 instead, because it is possible, then we have 2 times, oh, right, I did this, no, that's correct. Okay, so negative 4 to the fifth power, it is an odd power, so it's going to be negative. So we'll get negative 2048. So the magnitude of the numbers are the same, but the signs are different, which is understandable because every second term, the signs are different, as you can see. Again, this is a unique example. Generally, um, there will be ways to avoid this kind of ambiguity on an assignment or test. All right, let's move on to part B. The last term of the sequence is 524,288. All right, so it's a little bit tricky. The nth term is 2. What? One sec. Actually, we're just gonna write it this way: the first term and then r to the n minus 1 power, and then we can substitute what we know. We know that the nth term, the last term, is 524,288. The first term is a 2. And to keep it simple, we're just going to use the positive 4 as our r value here. And then n minus 1. Okay, we can divide both sides by 2 here. That will give us 262,144 is equal to 4 to the n minus 1 power. Now, unfortunately, we don't have a good way of finding n in this case. So we do have to do a little bit of guess and check here. Later on in this course, there will be a better way of doing this, but for now, we will just guess and check. Okay, and so what we'll find is that 262,144 is equal to 4 to the 9th power. Again, guessing and checking. So 4 to the 9th power is got to be equal to 4 to the n minus 1. That means 9 is equal to n minus 1, which means n is equal to 10. So that will be the 10th term then. Okay, so notice that since here the 10th term is positive, then r must have been positive as well, which kind of gets rid of the ambiguity that we saw in part A, but it's kind of counterintuitive how it works. Like we have to do part B to determine which r was in part A. That's generally what we don't want to see in questions because it gets very confusing. So again, we will try to avoid the ambiguity around the r values. It's going to be one or the other. It's not going to be both positive and negative 4. Anyways, but it is good that we did see it kind of an ambiguous case here, so you know that could happen. Example 3, let's see. Dr. Banner, gamma rays to become the Hulk. Body weight increased by 12% per second when transforms into the Hulk. Dr. Banner weighs 80 kilograms when the transformation begins. How much does he weigh after 1 minute? All right, so we know that the first term is 80. And the ratio, common ratio, is 1.12. Now, why is it 1.12, you might ask? Well, it's 100% and then a 12% increase. So that's 112% or 1.12. That's our common ratio. Okay. So if we are to find the final weight, then this will be 80 times 1.12 raised to the 60th power, which is equal to, might have to round here. Use a calculator for this part. Okay, let's round it to the nearest kilograms and we'll get 71 1,808 kilograms. Okay, so it's a good way to introduce common ratios that are not just fractions or integers. It's also possible to have common ratios that are decimals. As I said earlier in the notes, common ratio can be basically any real number. Okay, so that's it for today. Thank you for listening.